In this video, we are going to have an illustration showing the necessity of choosing gamma in F such that A plus gamma B is not equal to AI plus gamma Bj for j not equal to 1 and for any value of I such that you have your f of C as f of AB where C is this A plus gamma B. So it is not actually a verbatim proof of this theorem, um, primitive element theorem, where we prove that if A and B are algebraic, then you can find one C in f of AB such that f of C is equal to f of AB. So it is not a verbatim proof of that theorem, but we are going to give an explanation with an example that why we should not have A plus gamma B. Rather, with lambda, we say that A plus lambda B equals AI plus lambda Bj. Why that should not be there? So only for that, this explanation with the example that we consider. Now, we will take A to be cube root of 2 and B to be cube root of 3. Of course, our F is the base field, the field of rational numbers. Now, we can easily see that A satisfies the irreducible polynomial x cube minus 2 of degree 3 over q. And similarly, B satisfies the irreducible polynomial x cube minus 3 of degree 3 over q. Now we'll consider the roots of this. We shall take as f of x and this one will take as g of x. Now we'll consider the roots of f of x, namely cube root of 2, cube root of 2 omega, cube root of 2 omega square, where omega is minus 1 plus I root 3 by 2. Similarly, the 3 cube roots of this one g of x will consider as cube root of 3, cube root of 3 omega and cube root of 3 omega square. This is for g of x and this is for f of x. We'll name them as a1, a2, a3, b1, b2, b3, and this is what for which that we are going to find C such that f of A comma B is f of C. What is the primitive element? So we are taking A1 as A and B1 as B. Now if you consider these two polynomials, the splitting field of these two polynomials together, when we consider, it should be only this. We'll have to have f along with A, B and omega. So this is an extension of f in which both of this split completely. Splitting field of these two polynomials. F of A is only splitting field of we cannot even say that it is splitting field of this. So for both together means we need to consider. If you want to have for this alone, then a cube root of 2, that is A omega. For this alone means B omega, f of B omega. For both of them together, when we consider, it is L. So L is the extension of f in which these two completely split. Now we claim that there are only finite number of lambdas in L such that A plus lambda B equals AI plus lambda Bj for j not equal to 1. Now actually having got I and j ranging between 1 and 3, when we construct the table, the pairs that what we get for Ij, ordered pair Ij is only this. 1 with 1, 1 with 2, 1 with 3, and similarly 2 with 1, 2 with 2, 2 with 3, 3 with 1, 3 with 2, 3 with 3. So these are the pairs that we get. Now these are ruled out for the reason that j should not be 1. According to this, j should not be 1. If j is equals 1, then you will have this having some finite number by 0, even when you consider this 0 by 0 form. So to avoid that, here itself we are saying this. So in the table, there is no need to consider these cases. So we are left with only these cases, of which when we consider 1, 2 and 1, 3, we will get lambda to be 0. That we will see now. So for the 9 values of ij, we compute lambda. See, what we have claimed here, there are only finite number of lambdas in L such that this one holds. This on simplification. Keep lambda one side, take the rest to the other side. So AI minus A, this one goes there. So B minus Bj, this is what your lambda is. Now for the 9 values, we compute lambda. Obviously, if I equals 1, then for ij equal to 1 and 2, 1, 3, lambda is 0. So if this is the case, lambda is 0 because a1 equals a. a1 equals a, so a minus a will give you 0. So when you have I to be 1, you will definitely get lambda to be 0. When lambda is 0, when you're choosing C as a plus lambda b, when you choose your C as a plus lambda b, when lambda is 0, this f of c becomes f of a. But f of a is properly contained in f of ab. So this cannot be your extension. I mean, you cannot have your f of ab to be equal to f of c. Ultimately, our goal is to have f of a comma b to be equal to f of c. So that cannot happen here, because when you consider this case, you will have this to be f of a alone, because lambda becomes 0, so f of c becomes f of a. So this only will imply that your f of a is, I mean, this implies that f of a is properly contained in f of ab, which we don't require. F of c is f of c is properly contained in f of ab. F of c is properly contained in f of ab. Right. Now, if we consider, as I said earlier, when you have this one second component to be 1, automatically this cannot exist, so it is not defined. So that also we are ruling out. Now we find lambda for the rest, that is for these. Even in that, we will finish off this case first and then go to this. So when ij is this pair 2 comma 2, a2 minus a by b minus b2. a2 is taken as cube root of 2 omega, and this a is cube root of 2. And similarly, b is cube root of 3 minus cube root of 3 omega square is your um, that is not, this is just omega, not omega square, this is just omega. So omega, so that when you consider, when you simplify, you get cube root of 2 out, you get omega minus 1, and here 1 minus omega. So that gives you minus sign when you cancel this. So you have minus cube root of minus cube root of minus cube root of 2 by 3. Obviously, it's not a member of F, right? And so this lambda is only in L, it is in L. It is not in F, it is in L. Now, ij, when it is 3 comma 3, you have a3 minus a by b minus b3. Even in that case, with omega square minus 1, 1 minus omega square, cancelling that, you get the resultant, that is your lambda to be cube root of 2 by 3. Again, that does not belong to F, it belongs only to L. It belongs to L, and here also it belongs to L. So, again, we are left with these two cases. So, let us see what happens. Now, if ij equals 2 comma 3, this is what we get, and we are just substituting the values of a2, b3, a and b. So you get, taking this cube root of 2, cube root of 3 out, you get omega minus 1 in the numerator, and in the denominator 1 minus omega square. Again, it belongs to L, but it does not belong to F. This lambda belongs to L. This lambda also belongs to L. So, but they are not in F. So there exists finite number of lambdas in L, not in F. So these again, I said earlier, they are in lambda. Lambda belongs to L. Lambda belongs to L, but not in F, for which a plus lambda b equals ai plus lambda bj. Now, since characteristic of Q is 0, there exist infinite number of elements in Q. Our F is Q here. So, we can find a gamma in Q such that A plus gamma B is not equal to AI plus gamma Bj, with I and J not equal to this. Now, if you, in this particular case, remember our A is cube root of 2 and our B is cube root of 3. So only for this we want to have f of AB equal to f of C. What is that C? So that is our problem in this case. So when you take C as cube root of 2 plus gamma cube root of 3 with gamma in F, of course gamma should not be 0. Gamma should not be 0. So, but in most of the cases, this gamma will be 1. So that you will have this one to be this. See, I have said already that this is not a verbatim proof of that primitive element theorem. What is the necessary to choose your gamma so that this does not happen? That is, this equal to this one does not happen. We want to have only this to happen. A plus gamma b not equal to this. Why it has to be insisted? So only for that this illustration that we are giving, not for the verbatim proof of, or not for the verbatim illustration for that proof. The rest of the steps what we had in that proof can easily be seen with the same example. So that could be easily understood from the theorem proof itself. So this is the part where the students get confused. So only for that this video is given. Thank you.